The process begins with the raw materials, steel coils. These coils are typically stored in large warehouses. To start the manufacturing process, a magnet lifter is used to safely and efficiently transport the steel coils to the next processing stage. Once the steel coils are in position, they go through an edge milling machine. This machine is designed to remove any irregularities or imperfections from the edges of the steel strip, ensuring a smooth and uniform surface. It also trims the edges to the required width. After edge milling, the steel strip is passed through a pre-bender machine. This machine pre-bends the edges of the strip to the desired curvature, making it easier to form into a circular shape in later stages. The pre-bent steel strip is then fed into the infeeder machine. This machine guides the strip into the next critical step, the JCO, J-ing, C-ing, and O-ing press bending machine. This machine takes the pre-bent steel strip and transforms it into the fundamental U-shaped configuration. The hydraulic forces exerted on the steel strip gradually mold it into this U-shaped form, laying the foundation for the eventual creation of the pipe. The accuracy and consistency achieved by the JCO press bending machine are essential for ensuring that the pipes meet strict dimensional and structural requirements, ensuring their integrity and performance in various applications. Once the U-shaped steel is formed, a turning transfer car moves it to the next stage. This car rotates the steel section to prepare it for welding. In this step, the U-shaped steel is tack welded along its length. Tack welding holds the steel section in its circular shape temporarily, allowing for further processing. The tack-welded steel section is then passed through an inside welding machine. This machine creates a continuous weld seam along the inside of the steel section, ensuring a strong and leak-proof joint. After the inside welding, any excess weld material or imperfections are removed using a back bead cutting machine. This step ensures a smooth interior surface, which is essential for efficient fluid flow and reduced friction. The exterior welding process is similar to inside welding, but is done on the outer surface of the steel section. It creates a continuous weld seam along the outside, strengthening the pipe's structure. The impending machine, often referred to as the A-way machine, is used to further refine the shape of the steel pipe. It ensures the pipe is perfectly round and meets the required dimensions. To prepare the pipe ends for connection or welding with other pipes, an end-facing machine is employed. It trims and bevels the pipe ends to the specified angle and dimensions. Before proceeding to the final inspection stage, the pipes go through a washing device to remove any contaminants and ensure cleanliness. Pipes are examined for any internal defects, weld quality, and dimensional accuracy using X-ray technology. This ensures that the pipes meet the required quality standards. After successfully passing the X-ray test, the steel pipes are ready for packaging and shipment to customers. This comprehensive manufacturing process guarantees the production of high-quality steel pipes that meet industry standards and perform reliably in various applications.
The production begins with the automatic feeding of bars into the production line. A specially designed magazine ensures a continuous supply of bars, which are the initial raw material for the bullet shell manufacturing process. The bars are then subjected to inductive heating using the BBS_Brown Boveri installation. This installation, with a power of 1,450 kilowatts and a heating frequency of 500 Hz, employs electromagnetic induction to heat the bars uniformly. This controlled heating process enhances the malleability of the steel bars, making them more amenable to subsequent shaping. The heated steel bars, now pliable, are passed through a FICEP hydraulic press shear. This hydraulic press shear is equipped to cut through bars with diameters of up to 130 millimeters. This step is crucial in obtaining uniform lengths of the heated bars for further processing. The cut bars are then forwarded to the EUMUCO hydraulic press, where the actual forging of the steel shell casings takes place. This press consists of 2 units working in tandem. One unit of the EUMUCO press focuses on compression and push broaching. With an impressive force of 630 tons and a drop hammer traverse of 1,250 millimeters, this unit shapes the heated steel into preliminary casing shapes. The intense force exerted ensures the formation of accurate and precise designs. The second unit of the EUMUCO press is responsible for the drawing process. Equipped with rolls and rings, this unit calibrates the forged shell casings to achieve the desired dimensions. The force applied is 200 tons, and the drop hammer traverse extends to 3,200 millimeters, allowing for intricate shaping. Once the forged shell casings are shaped, a robotized stacker arranges the hot casings onto pallets. This automated stacking process ensures efficient and consistent arrangement, preparing the casings for normalization. The normalized shell casings then proceed to a line dedicated to their mechanical processing, where precision and accuracy are paramount. Within this line, the GF programmable hydrocopying lathe takes center stage. This advanced machine is designed for shell casing turning with exceptional efficiency. The lathe's programmable nature allows for precise control over the turning process, ensuring uniformity and quality across all casings. The last step in the mechanical processing line involves the final 131 programmable lathe. This lathe is dedicated to the final turning work on the inner side of the shell casings. It adds the finishing touches to the casings, preparing them for the assembly of bullets. To sustain the production flow, an automated magazine for billet charging is employed. This magazine ensures a constant supply of billets for processing, streamlining the entire production process. In an auxiliary roll, an EMA Elektro-Maschinen-Schultz GmbH inductive heating unit, with a power of 375 kilowatts and a frequency of 1,000 Hz, contributes to heating and shaping specific components of the bullet shells. For specialized bending of shell castings, the Usine de Wecker vibrating forging press comes into play. This press introduces controlled vibrations to achieve precise bends in the shell castings as needed. The journey of a razor blade begins with the pressing of raw materials. Typically, stainless steel strips are cut into smaller blanks, which are then subjected to a high-pressure pressing process. This initial step shapes the blanks into the fundamental blade structure. After pressing, the blades undergo a thermal process that includes heat treatment to enhance their hardness and durability. This controlled heating and cooling process, often referred to as annealing, helps optimize the blade's metallurgical properties. To achieve the razor-sharp edge that consumers expect, the blades must undergo precise edging and polishing. Advanced machinery and abrasive materials are used to refine the blade's edge, ensuring it is both sharp and smooth. Quality control is paramount throughout the production process. Skilled technicians inspect each blade for defects, imperfections, or deviations from the required specifications. Blade coating is an important step that enhances the blade's performance and prolongs its life. Sintering is a critical process that involves heating the blades to high temperatures to further strengthen the metal's crystalline structure. This step ensures the blade remains durable and sharp throughout its lifespan. To guarantee the blades meet stringent quality criteria, a sharpness test is conducted. This test measures the blade's cutting ability, ensuring that it can provide a close and comfortable shave without causing irritation or nicks. Razor blades are susceptible to corrosion, which can significantly reduce their lifespan. To prevent rusting, the blades are carefully soaked in anti-rust oil. This protective coating ensures the blades remain in pristine condition until they reach the hands of the consumer. Once the blades have passed all quality checks and treatments, they are carefully packaged. Packaging materials are chosen to maintain the blade's hygiene and sharpness until they are opened and used by the consumer.
Once the steel sheets are flattened, they are cut into specific sizes according to the required drum dimensions. This is usually done using a shearing machine or a laser cutting machine. The cut sheets are then transferred to a forming machine, where they are shaped into cylindrical bodies. The forming machine utilizes a series of rollers and presses to shape the sheets accurately. The first step is to design the lid according to the specifications and requirements of the barrel. This includes determining the lid's dimensions, shape, and any additional features such as handles or vent holes. The iron sheets are fed into a stamping press, which consists of a hydraulic or mechanical system capable of exerting high pressure. Once the initial stamping is complete, the lid may require additional processes such as trimming and piercing. Trimming removes any excess material from the edges of the lid, ensuring a clean and precise shape. After stamping, the lids undergo surface treatment to protect them from corrosion and enhance their appearance. The surface treatment can include cleaning, degreasing, and applying coatings such as paint, powder coating, or galvanizing. After the cylindrical bodies are formed, the next step is to join the two ends of the body to create a drum. This is done through a process called seaming. The edges of the cylindrical bodies are folded and interlocked, creating a secure and leak-proof joint. The seaming process is usually automated, using specialized seaming machines. In addition to seaming, welding may also be employed to strengthen the joint further. Once the seaming process is complete and the cylindrical body of the steel drum is formed, it requires the addition of a bottom and top ring for structural stability and reinforcement. These rings play a crucial role in ensuring the overall integrity and durability of the drum. The bottom and top rings are typically made of thicker gauge steel compared to the drum body. This is done to provide enhanced strength and rigidity to the drum, as the rings are subjected to significant stress and impact during handling, stacking, and transportation. In this stage, the various components of the steel drum, including the body, bottom and top rings, closure mechanisms, and handles, are assembled. The closure mechanisms can include various options such as bolted rings, lever lock closures, or drum plugs. Once assembled, the drums undergo rigorous testing to ensure their integrity, including leak testing, pressure testing, and load testing. Before painting, the barrel's surface needs to be properly prepared. This typically involves cleaning and removing any dirt, oil, rust, or old paint. Surface preparation can include methods such as sandblasting, chemical cleaning, or mechanical abrasion to ensure a clean and smooth surface. To enhance adhesion and improve paint durability, a primer is applied to the surface. The primer acts as a bonding agent between the metal surface and the paint layer. It also provides additional protection against corrosion. The primer is evenly sprayed or applied using a brush, ensuring complete coverage. Once the primer is dry, the actual paint is applied to the barrel. The paint can be applied manually using brushes or spray guns, or it may be done through automated processes such as electrostatic painting. Multiple coats may be applied to achieve the desired thickness and color. Each coat is allowed to dry before the next one is applied.
Battery recycling is an essential process for recovering valuable resources and reducing environmental impact. Although the path to battery recycling can be complex, efforts are being made to establish collection systems and recycling facilities. After this initial sorting, the different types of batteries are further sorted manually. Lead batteries are separated from lithium batteries, and consumer batteries, including both non-rechargeable primary batteries and rechargeable secondary batteries, make up the majority of the batteries treated in this facility. Consumer batteries contain specific chemical elements, nickel hydride, which are in high demand in the market. To make the battery recycling process economically viable, large quantities of batteries are required. Therefore, the more batteries that are collected, the greater their value. During the sorting process, any electronic waste, cable foils, and foreign materials that are not part of the battery composition are removed. Even small button batteries containing mercury are sorted out and processed separately. Once the batteries have been sorted, the consumer batteries are further separated based on their metal content, including alkaline, iron, zinc, and manganese. The recycling process begins by filling each group of consumer batteries into containers, which are then mixed in equal proportions. The container mixture is subjected to pyrolysis in an oven heated to 700 degrees Celsius. During this process, certain ingredients are dissolved from the battery materials, water evaporates and is removed, and paper, plastics, and coal burn. To ensure safety, highly toxic furans and dioxins are filtered out. Through pyrolysis, valuable materials are obtained. Zinc, which constitutes around 23% of a consumer battery, is skimmed off and processed in zinc smelters. The extracted zinc has its own value listed on the stock exchange. In some batteries, mercury is released during pyrolysis, and it is captured in filters. Due to its highly toxic nature, mercury must be treated separately. In a separate facility, the mercury is separated from the filters and button batteries, and it is collected in its pure form for return to the industry. After pyrolysis, consumer batteries may appear as charred scraps since some materials have already been removed. However, they are valuable homogeneous materials. A final processing step takes place in another melting furnace, which reaches a temperature of 1500 degrees Celsius, twice as high as the first facility. At this point, the molten metal is tapped by workers wearing asbestos protective clothing. The molten mass flows into molds and cools within minutes. The resulting product is a metal alloy called ferromanganese, composed of iron and manganese. Ferromanganese is commonly used in the metal industry to regulate the hardness of steel. This intricate process begins with a metal blank, the starting point for all parts. Skilled metalworkers kick off the transformation in a potent electric melting furnace where steel is rapidly heated to extreme temperatures. Within seconds, the metal reaches a malleable state, ready for its metamorphosis. Subsequently, the heated steel is carefully placed onto a stamped mold, and an immense press exerts tons of force, shaping the blank into the desired form. It's a meticulous process that may require up to 4 strikes for each blank to achieve its final shape. The next phase focuses on creating the essential teeth on the pliers' jaws. Workers insert the plier halves into a specialized machine equipped with tiny sheets of steel. Here, dozens of these tiny teeth are meticulously cut using a high-speed stream of coolant. As the halves emerge from this process, they already possess a finely serrated set of teeth. To ensure the pliers' strength and durability, they undergo a crucial heat treatment process known as tempering. The plier halves spend a grueling 2 hours inside a gas furnace, where temperatures soar beyond 800 degrees Celsius. Following this, they are rapidly and uniformly cooled by immersion in salty water. These teeth on the pliers, designed to withstand heavy-duty tasks, receive additional fortification through laser treatment, enhancing their hardness and toughness. Now the pliers are ready for the assembly phase. Creating a pair of pliers is relatively straightforward. A worker inserts a pivot and joins both halves. Then, the pivot is securely fastened at high speed using a machine that applies significant force and friction. The process differs slightly for slip joint pliers. These tools undergo a unique treatment, beginning with placement under a press that employs heat and high pressure to firmly clamp the pivot. Workers then insert the slip joint pliers between two grinding wheels using an emulsion to prevent overheating. The pivot is ground down until it becomes level with the surface of the pliers. Subsequently, these pliers are sent to a gas furnace for another 2-hour heat treatment, a crucial part of the tempering process. After removal from the furnace, they are immersed in an oil solution, a departure from the rapid cooling in salty water employed for regular pliers. Steel is an exquisite material, making meticulous heat treatment essential to avoid compromising its quality. Post-heat treatment, the pliers are immersed in a bath filled with an anti-corrosion solution, safeguarding the steel from rust while lubricating the pivot. A robotic arm takes charge, lifting the pliers to a grinding belt that smoothens all surfaces except the handles. Subsequently, the company's logo and product number are etched onto the pliers with precision using a laser. Before dipping into liquid vinyl, hundreds of pliers are preheated to ensure the coating adheres seamlessly to the steel. This protective coating hardens when exposed to heat and remains on the handles, enhancing their grip and usability. The first step in the wrench manufacturing process is the selection of the appropriate raw materials. Wrenches are typically made from high-strength steel alloys. The choice of material depends on the desired properties of the wrench, including strength, durability, and resistance to corrosion. Alloy steel is a common choice due to its excellent balance of strength and toughness. The forging process is a critical step in the production of wrenches. After carefully selecting the raw steel materials, they are subjected to intense heat, typically at temperatures exceeding 2000 degrees Fahrenheit, 1093 degrees Celsius. This extreme heat makes the steel more malleable, allowing it to be shaped with precision. Once at the correct temperature, the steel is placed in specialized dies and subjected to immense pressure. This pressure forces the steel into the desired shape, aligning its grain structure in the process. This alignment enhances the mechanical properties of the steel, significantly increasing its strength and durability. After forging, the rough wrench blanks undergo chemical grinding. This process involves removing excess material and refining the shape of the wrench heads. Chemical grinding ensures that the wrenches have precise dimensions and a smooth, uniform surface. Polishing follows chemical grinding, where the wrenches are carefully smoothed to achieve a high-quality finish. This step not only enhances the wrench's appearance, but also prepares the surface for subsequent processes, such as plating. Stamping is a crucial step in the wrench manufacturing process, as it involves imprinting important information on the wrench, such as the brand name, model number, and size. This information is essential for product identification and traceability. Heat treatment is another critical process used to enhance the mechanical properties of wrenches. Wrenches are heated to specific temperatures and then rapidly cooled to achieve the desired hardness and toughness levels. Proper heat treatment ensures that the wrenches can effectively grip nuts and bolts without breaking or deforming. Sandblasting is employed to prepare the surface of the wrenches for plating. This process involves propelling abrasive particles against the surface at high velocity, effectively removing any remaining impurities and creating a textured surface that promotes adhesion during the plating process. After sandblasting, another round of chemical grinding may be necessary to refine the surface further. This ensures that the wrenches are free of imperfections and have a smooth, uniform finish. In this step, the open end of the wrenches is precisely ground to create the distinctive profile and functional features. Open-end grinding ensures that the wrenches have the correct geometry for effectively gripping nuts and bolts. Prior to plating, the wrenches undergo a thorough cleaning process to remove any residual contaminants, oils, or residues. This step is crucial to ensure the plating adheres properly and produces a durable, corrosion-resistant finish. Plating is a critical surface treatment that enhances the wrench's corrosion resistance and appearance. Chrome plating, for example, not only provides a protective layer but also imparts a shiny finish to the wrenches. Different plating methods and materials may be used based on the specific requirements of the wrenches and market demands. Quality control is paramount in the wrench manufacturing process. The finished wrenches undergo rigorous testing to ensure that they meet specified standards. Testing may involve dimensional measurements, hardness testing, torque testing, and visual inspections. Each wrench must pass these tests to ensure that it will perform reliably in various applications. Once the wrenches have passed all quality checks and inspections, they are carefully packaged for distribution. Packaging methods can vary depending on the intended market and customer preferences.
The process begins with a round bar, or preform, which is heated to the appropriate forging temperature. The heated material is then fed into the ring blank press, where it undergoes several operations. The press exerts immense force to compress and shape the material into a cylindrical shape, thereby forming the initial ring blank. The ring forging machine Radial 005001, manufactured by SMS Meergum, is a highly advanced piece of equipment used for the process of ring rolling. This particular machine, in conjunction with Axial profiling technologies, allows for efficient and precise production of seamless rolled rings. Let's delve into the working mechanism of the Radial 80050001 in detail. The ring rolling line, known as Radial 8500s, consists of various components working in tandem to produce high-quality rolled rings. One crucial component is the ring blank press, type SRP 8000 liters. The purpose of this press is to shape the raw material into a ring blank with the desired dimensions and properties. Once the material reaches the desired temperature, typically through heating in a furnace, it is ready for the next step in the ring rolling process. The heated workpiece is carefully placed into a specialized machine known as a ring blank press. The ring blank press is designed to apply immense pressure to the heated material, using a series of compressive forces. The workpiece is positioned between two die halves or platens within the press. As the press closes, the material is subjected to extreme pressure, causing it to deform and take on a cylindrical shape. This intense pressure facilitates the formation of the initial ring blank with the desired dimensions. The pressing operation in the ring blank press is crucial in shaping the material accurately and achieving the required cylindrical form. The amount of pressure applied and the duration of the pressing process are carefully controlled to ensure the workpiece reaches the desired shape while maintaining the necessary structural integrity. The ring blank press plays a vital role in the initial stages of the ring rolling process, providing the foundation for subsequent steps. Once the ring blank is formed, it is transferred to the ring rolling machine, where it undergoes further deformation and shaping to achieve the final rolled ring product. Once the ring blank is formed, it is transferred to the radial axial ring rolling machine, known as RA 50063040050080001700. This machine plays a pivotal role in the actual ring rolling process. The ring blank is placed on a mandrel, and the rollers apply radial and axial forces to gradually deform and shape the blank into a seamless rolled ring. The utilization of axial profiling technology in the RIWA 80005001 enables precise control over the geometry and cross-sectional shape of the rings. The machine is equipped with advanced sensors and computerized controls that continuously monitor and adjust the rolling process in real time. This ensures consistent quality and accurate dimensions for the finished rings. Throughout the ring rolling process, the RA 50063040050080001700 machine rotates the mandrel, while the rollers move in a synchronized manner. The rollers progressively decrease the height and increase the diameter of the ring as it progresses through the machine. This controlled deformation results in a ring with precisely controlled wall thickness and diameter. The axial profiling technology also permits the production of complex shapes and profiles within the rolled rings. By adjusting the axial forces and roller movements, the machine can create flanges, grooves, and other intricate features as per the desired specifications. The RIWA 80005001, designed for high productivity, boasting a rolling capacity of up to 8,000 mm in diameter and 500 mm in height. The machine operates at high speeds, facilitating efficient production of rings in both large and small sizes. Watering is usually done through watering systems integrated on the rolling mill. Water is sprayed onto the material and the contact area between the material and the rollers to ensure effective cooling and lubrication. Through the use of water, ring rolling can be performed with high efficiency, and a better final winding quality is achieved.
The steelmaking industry is known for its rigorous demands on equipment reliability, product quality, and overall plant availability. In this context, robust and dependable drive technology plays a crucial role in achieving high-quality steel products and ensuring uninterrupted plant operations over decades. One company that has excelled in this field is SMS SEMA, which specializes in the development, design, and manufacturing of drive systems and components for steelmaking plants and rolling mills. SMS SEMA's drive solutions are a product of the synergy between metallurgical plant know-how, rolling mill technology, and cutting-edge gear design. The company's commitment to quality and innovation is reflected in its product range, which encompasses all drive systems required for both hot and cold rolling mills, as well as steelmaking plants. A cornerstone of SMS SEMA's approach is its emphasis on producing essential drive components in-house. Their main drive gears, mill pinion gears, twin drive gear units, and other critical components are developed and manufactured entirely at their facilities in Germany. This vertical integration allows the company to maintain strict quality control and ensure short delivery times for their customers. Recent investments of over 80 million euros have been directed towards expanding SMS SEMA's Hiltonbach workshop. This expansion includes the establishment of a new gear-making shop, which consolidates major manufacturing steps for large gear units. With state-of-the-art machinery, this workshop can fabricate gears with modules up to 40 and diameters up to 6 meters. The manufacturing process starts with mechanized submerged arc welding, followed by stress relief and precision milling under qualified supervision. The case hardening process is a pivotal step as it imparts durability to the gears. This is exemplified by the case hardening of a double helical spur gear weighing approximately 45 metric tons and boasting a diameter of 4.5 meters. Ultrasonic testing of gear teeth ensures their quality, followed by tooth flank grinding on profile grinders. The resulting gears undergo high-precision testing on dedicated gear measuring machines. SMS SEMA's commitment to excellence extends to gear housings, which are also produced in-house. The entire gear unit is pre-assembled, and gear contact patterns are meticulously adjusted using eccentric sleeves. These sleeves, controlled by computer-aided programs, enable precise adjustments of the gear contact pattern and tubing clearance even after years of operation. The testament to SMS SEMA's expertise lies in its ability to offer tailored modernization solutions. At Alaris Aluminum in Koblenz, Germany, the company replaced the entire drivetrain within a few days. The highlight of this revamp was the installation of a twin-drive gearbox without interrupting plant operations. The new drive and motors were mounted on a foundation block and moved seamlessly to replace the old drive unit after successful function tests. SMS SEMA's drive components are designed according to stringent in-house standards using advanced tools, including 3D CAD systems and specialized calculation programs. The company's well-structured work schedules and production control interfaces facilitate rapid implementation of designs. Production is carried out by highly qualified and experienced employees, many of whom have completed vocational training with SMS EEMA. Comprehensive service plans offered by SMS SEMA ensure ongoing drive performance. These plans encompass extensive inspection services and monitoring systems that utilize temperature, torque, and vibration data for preventive maintenance. From development and design to in-house manufacturing, assembly, project management, electrical and automation systems, and after-sales service, SMS SEMA offers comprehensive drive engineering solutions from a single source. SMS SEMA stands as a paragon of drive technology excellence in the steelmaking and rolling mill industry. Their integrated approach, investment in cutting-edge facilities, and commitment to quality ensure that their drive solutions not only meet the highest demands, but also contribute to the sustained competitiveness of their customers. Through a combination of process knowledge and gear design expertise, SMS SEMA paves the way for top-quality products and the seamless operation of steelmaking plants and rolling mills for generations to come.
The company maintains an impressive production capacity, churning out between 1 million and 1,100,000 machetes each month. Their self-sufficiency in sourcing materials is evident, with steel primarily imported from England or Korea. This steel undergoes a meticulous transformation process, encompassing cutting, marking, rolling, learned from their German partners, forming heat treatments, tempering and quenching, polishing, sharpening, individual straightening, lacquering for rust protection, packaging, and sales. With a workforce of around 900 to 910 employees, Colma's core focus lies in safeguarding its market share in Colombia's machete market. Although their ultimate aim is global expansion, they have tailored approximately 850 machete models to cater to the unique preferences of farmers worldwide, prioritizing customer familiarity, quality assurance, competitive pricing, and adaptability to regional variations. Colma's export markets have solid roots in Latin America and extend into emerging markets like Africa and other regions. Their global reach encompasses Ivory Coast, Ghana, Liberia, South Africa, Papua New Guinea, Namibia, Lithuania, the Democratic Republic of the Congo, with potential prospects in New Caledonia, Fiji, and Equatorial Guinea. They proudly claim the title of the world's largest individual machete plant. The manufacturing process begins with the selection of high-quality raw materials. Specialized steel wire, known for its strength and durability, is used as the base material. This wire is meticulously inspected for any defects or impurities before it proceeds to the next step. Next, the steel wire is passed through a series of machines that shape it into a razor blade form. This process involves precision cutting and welding to create the distinctive razor-like barbs. These barbs are designed for both practical functionality and aesthetic appeal, ensuring the final product not only provides security, but also looks visually appealing. Once the razor blades are formed, they are welded onto a wire mesh to create the razor mesh fence panels. The mesh spacing and the density of the razor blades can be customized to meet the specific needs of customers. This flexibility allows for the production of fence panels suitable for various applications, including guarding fences, doors, windows, and military installations.
The manufacturing process begins with the preparation of the raw materials required for bearing production. These materials include steel or ceramic for the bearing rings, rolling elements, and cages. The materials undergo strict quality checks to ensure they meet the required specifications. The prepared materials are then subjected to machining process etching, grinding, and milling. These processes shape the components to their desired dimensions and surface finish. After machining, the bearing components undergo heat treatment processes to enhance their mechanical properties. Heat treatment techniques like quenching and tempering are applied to improve hardness, strength, and resistance to wear and fatigue. During the assembly of bearings, each component is meticulously handled to ensure precise alignment and optimal performance. The inner and outer rings, which encase the rolling elements, are carefully fitted together to create the bearing structure. The rolling elements, such as balls or rollers, are precisely positioned within the rings to enable smooth and efficient rotation. The cages, made of steel or synthetic materials, maintain proper spacing and guidance for the rolling elements. Special attention is given to lubrication during assembly to reduce friction and prevent premature wear. Proper alignment and lubrication are essential factors in ensuring the longevity and reliability of the bearings. Once the bearings pass the quality control tests, they are packaged securely to protect them from damage during transportation. The first step in the manufacturing process is the careful selection of balls. The balls used in Zen bearings are typically made of high-quality steel or ceramic materials. These balls must meet strict specifications in terms of size, roundness, and surface finish. They are carefully inspected and sorted to ensure uniformity and consistency in performance. Once the balls have been selected, the next step is to join the inner and outer rings of the bearing. The rings are typically made of steel and are precision machined to the required specifications. They are then carefully assembled using advanced techniques such as precision welding or press fitting. This process ensures a tight and secure fit between the rings, providing stability and durability to the bearing. After the rings are joined, the balls are fitted into the raceways created between the inner and outer rings. This step is crucial for achieving smooth rotation and minimizing friction. The balls are evenly distributed around the raceways, and their size and position are carefully controlled to ensure optimal performance. Advanced machinery and precise measurement tools are used to achieve accurate ball fitting. The final step in the manufacturing process is the precise spacing of the balls. This step is critical to maintain the proper alignment and balance of the bearing. Special spacers or cages are used to separate the balls and maintain a consistent distance between them. This ensures that the balls roll smoothly and evenly distribute the load, enhancing the overall performance and longevity of the bearing. The process begins with the loading manipulator, which carefully positions the raw material, known as the blank, in the exact center of the press dies. Once in position, the press, boasting an incredible 9,000 tons of pressing force, initiates the forming process. The stroke of the press upsets the blank, shaping it into the desired profile for the wheel rolling process. This crucial step sets the foundation for the subsequent stages of production. After the forming process, the sliding table moves the profile blank for further processing. At this point, the first transfer manipulator comes into play, removing the blank from the press and transferring it to the next phase. Automation takes center stage as 3 industrial robots take charge of cooling and lubricating the press's controlled axes. This ensures smooth and efficient operation during the entire production cycle. During the rolling process, the wheel blank is guided solely by web rolls, pressure rollers, and lateral rolls, without the need for a mandrel. This state-of-the-art wheel rolling technology optimizes material flow and enhances the overall quality of the wheels. Additionally, the system allows for online adjustments to the tool settings, enabling real-time optimization of the production process. The press dies undergo automatic cooling and lubrication, facilitated by advanced technology. Furthermore, a marking device equipped with an innovative needle embossing tool adds identification text to each wheel. An oscillating needle precisely embosses the required markings, ensuring accurate and reliable identification throughout the wheel's lifespan. Once the wheel is marked, it is transferred to the wheel measuring machine. The latest 3D laser technology is employed for precise and comprehensive measurements. This advanced measuring process captures every intricate detail, ensuring that the wheels meet the highest quality standards. An automation and piece tracking system continuously monitors the production, documenting and archiving the product quality for future reference. The Rolltech Wheels technology software plays a vital role in this automated production line. It ensures the perfect setting of the forming machines, allowing for maximum efficiency and precision. With this seamless integration of technology, the system has the capability to produce an impressive 280,000 wheels per year. These wheels have outer diameters ranging from 700 to 1,350 millimeters, catering to various railroad applications.
The foundation of any high-quality rail steel shovel is the raw materials used. Typically, these shovels are made from high-grade steel, often referred to as rail steel due to its origins in the railway industry. This steel is specifically chosen for its exceptional strength, toughness, and resistance to wear and tear. The primary constituents include iron, carbon, and various alloying elements like manganese and chromium. The specific composition may vary depending on the manufacturer's preferences and the intended use of the shovel. This high level of cleanliness is a testament to the precision and effectiveness of the shot peening process and makes the coil springs ready for subsequent processing steps, such as powder coating or any other finishing processes required. The first step in shovel production involves melting the raw materials to create a molten steel alloy. This process occurs in a specialized facility, such as a steel foundry, where precise control of temperature and composition is crucial. The molten steel is then poured into molds to create the shovel's initial shape. This can be done using various casting methods, including sand casting or investment casting, depending on the manufacturer's techniques and capabilities. Once the initial shape is achieved through casting, the shovel undergoes a critical step: forging. Forging involves shaping the shovel further by applying pressure and heat. This process not only refines the shovel's form but also enhances its mechanical properties, making it more durable and resistant to bending or breaking. After forging, the shovel is subjected to a heat treatment process that involves controlled heating and cooling cycles to optimize its hardness and toughness. After heat treatment, the shovel's surface is machined to achieve precise dimensions and smoothness. This step ensures that the shovel meets the required specifications for its intended use. Additionally, it may involve the creation of special features such as serrated edges or reinforced handles, depending on the shovel's purpose. To protect the rail steel shovel from corrosion and enhance its aesthetics, it is often coated or painted. This may involve the application of a rust-resistant coating, such as zinc or epoxy, which helps extend the tool's lifespan, especially when exposed to harsh outdoor conditions. Painting is typically done for branding and visibility purposes. Throughout the production process, strict quality control measures are in place to ensure that each shovel meets the highest standards. This includes dimensional checks, hardness testing, and visual inspections. Some shovels may also undergo specialized testing, such as impact testing, to assess their resilience under extreme conditions. After the steel has been cut and shaped, it undergoes a heat treatment process to enhance its mechanical properties. This step is crucial to achieving the desired spring characteristics. Heat treatment involves heating the steel to specific temperatures and then rapidly cooling it to achieve the desired hardness and resilience. In the case of parabolic springs, the workpieces are cleaned and descaled to remove any impurities or surface imperfections that may have occurred during the previous steps. The cleaning process ensures that the surface of the springs is ready for shot peening. Shot peening is a pivotal stage in the manufacturing process of parabolic and coil springs for rail vehicles, as it imparts additional strength and durability to these crucial components. At the onset of shot peening, the springs, which have undergone prior heat treatment and cleaning, are loaded onto a specially designed roller conveyor. This conveyor system is equipped with a closed-loop mechanism, meticulously designed to facilitate efficient loading and unloading of the springs. The closed-loop system ensures that the springs seamlessly transition through each step of the shot peening process. Once positioned on the roller conveyor, the springs are manually placed onto carriers. These carriers serve as the vessels that will transport the springs through the shot peening unit. To ensure that the springs remain firmly in place during the process, a protective cover is raised and secured over them. This step is vital to prevent any unintended movement or displacement of the springs, ensuring precise and consistent peening results. Before the shot peening process begins, an essential preparatory step involves applying pre-tension to the springs. A 20-ton press force is employed, combined with a 200mm upstroke. This pre-tensioning process readies the springs for the subsequent shot peening operation, ensuring they are properly prepared to withstand the blasting force and achieve the desired hardness level. As the springs embark on their journey through the shot peening unit, a network of sensors strategically placed along the roller conveyor comes into play. These sensors serve a critical role in ensuring the precision and consistency of the shot peening process. They automatically detect the position of the springs and activate the next steps in the process as needed, orchestrating a seamlessly coordinated workflow. The heart of the shot peening unit comprises high-performance turbines. Each of these turbines is rated at 22 kilowatts and plays a central role in delivering the blast media onto the springs. In this context, the blast media consists of rounded wire shot, chosen for its effectiveness in hardening the surfaces of the springs. The turbines precisely control the flow and direction of the blast media, directing it onto the tension side and edges of the springs. To maintain the integrity of the shot peening process, wear-resistant rubber curtains encase the area where the springs are being blasted. These curtains effectively prevent the escape of the blast media, ensuring that it remains focused on the springs to achieve the desired hardening effect. Additionally, noise protection booths are strategically installed in the vicinity to reduce noise levels, creating a more comfortable working environment and enhancing worker safety. An integral aspect of shot peening is the efficient management of blast media. Dust and undersized shot can accumulate during the process, potentially affecting its quality and efficiency. To counter this, a blow-off device is employed to remove any stray blast media adhering to the springs. This media is then returned to the shot peening process loop, ensuring a continuous and sustainable use of the blast media. The journey of coil springs through the shot peening process begins with an indoor crane. This heavy-duty machinery is responsible for transporting a batch of coil springs to the entry side of the specialized blast unit. Upon arrival at the entry side of the blast unit, a stair lift mechanism comes into play. This innovative device is designed to facilitate the separation and correct loading of the coil springs. It ensures that each spring is positioned appropriately for the shot peening process. 3. Parallel conveyors and lifting beam. To achieve uniform shot peening and ensure that every part of the coil springs is thoroughly treated, 2 parallel conveyors are employed. These conveyors work in tandem with a lifting beam, which is a critical component for delivering consistent results. The lifting beam provides the longitudinal motion necessary for precise shot peening. It is equipped with a frequency control gear motor, allowing for programmable transport speeds ranging from 1 to 4 meters per minute. The heart of the shot peening process lies in the high-performance turbines. In this specialized blast unit, 2 robust turbines, each rated at 22 kilowatts, come into play. These turbines are responsible for delivering the blast media, which in this case is rounded wire shot. The turbines are capable of generating the force needed to propel the blast media onto the coil springs, effectively cleaning and hardening their surfaces. One remarkable characteristic of coil springs produced through this process is their remarkable cleanliness. Shot peening not only imparts strength and durability, but also ensures that the springs are free from contaminants and surface imperfections. This high level of cleanliness is a testament to the precision and effectiveness of the shot peening process and makes the coil springs ready for subsequent processing steps, such as powder coating or any other finishing processes required.
Steel extinguishers are primarily made from high-quality steel, chosen for its strength, durability, and resistance to corrosion. The selected steel sheets undergo thorough quality checks to ensure they meet the required standards. The steel sheets are then cut into specific shapes and sizes according to the design specifications. These sheets are typically formed into 2 halves using hydraulic or mechanical presses. The halves are then welded together to create the cylindrical shape of the extinguisher shell. This welding process ensures a secure and leak-proof construction. A neck ring, made of steel or brass, is attached to the top of the extinguisher shell. The neck ring serves as a connection point for the valve assembly. The valve assembly consists of various components, including a pressure gauge, discharge lever, safety pin, and sealing gasket. Once the cylinders are formed, the seams are welded to create a seamless structure. Welding ensures the extinguisher is sturdy and airtight. The welds are carefully inspected to detect any imperfections or weak spots that could compromise the extinguisher's integrity. The steel extinguisher bodies undergo various surface treatments to enhance their corrosion resistance and aesthetic appeal. Before the extinguishers are ready for distribution, they undergo rigorous pressure testing to ensure their reliability and safety. The cylinders are filled with water or an inert gas, and then pressurized to a specified level. Before the painting begins, the extinguishers go through surface preparation to ensure optimal paint adhesion and a smooth finish. The surfaces are cleaned to remove any residual dirt, oil, or contaminants that might hinder the painting process. The manufactured steel extinguishers are distributed to various markets and customers. In many countries, these products must comply with specific safety standards and regulations set by national or international organizations. The first step in gas cylinder manufacturing is the selection of suitable raw materials. The most commonly used material for gas cylinders is high-quality steel, typically low alloy or carbon manganese steel. The steel possesses excellent strength, toughness, and weldability, making it suitable for withstanding high pressure. In the cylinder forming stage, the steel sheets are shaped into cylindrical bodies through a process known as deep drawing. This process involves placing a steel sheet over a die and applying force to draw the sheet into the desired shape. The deep drawing process typically consists of several stages to achieve the final cylinder shape. The first stage involves drawing the flat sheet into a cup-like shape, called a cupping operation. Subsequent stages involve redrawing the cup into a deeper shape, elongating it further. These redraws help in achieving the required dimensions and thickness of the cylinder. After the cylinder body is formed, the next step is to weld the seam to create a continuous structure. The welding process, commonly used, is the submerged arc welding saw technique. Saw provides a strong and reliable bond by melting the edges of the cylinder body and fusing them together using a flux cord electrode. Once the welding is complete, a neck ring is attached to the top of the cylinder. The neck ring serves as a connection point for the valve and provides additional strength to the cylinder. Heat treatment is a controlled process that subjects the cylinders to specific heating and cooling cycles. The primary objective of this step is to relieve any residual stress that may have developed during the welding process. Welding generates high temperatures and localized heating, which can introduce stress into the metal structure of the cylinders. If left unaddressed, this stress can compromise the integrity and performance of the cylinders. The heat treatment process typically involves two main stages: heating and cooling. The cylinders are carefully heated to a predetermined temperature, which allows the metal structure to reach a uniform temperature throughout. Once the desired temperature is reached, the cylinders are then subjected to a carefully controlled cooling process. This stage, known as quenching, involves rapidly cooling the cylinders in a controlled manner. Once the desired temperature is reached, the cylinders are then subjected to a carefully controlled cooling process. This stage, known as quenching, involves rapidly cooling the cylinders in a controlled manner. The specific temperature and duration of the heat treatment process vary depending on factors such as the steel composition, cylinder size, and intended application. The heat treatment process offers several benefits. Firstly, it helps to improve the strength and toughness of the cylinders, making them more resistant to external forces and impacts. Shot blasting is a critical process in gas cylinder manufacturing that prepares the surface of the cylinders for further treatment. It involves placing the cylinders in a specially designed chamber where they are subjected to a high-speed bombardment of steel shots or abrasive particles. The purpose of shot blasting is to remove any scale, rust, or surface contaminants present on the cylinders. These contaminants can hinder the adhesion of coatings and paints, compromising the overall quality and performance of the cylinders. The roughened surface created by shot blasting serves multiple purposes. Firstly, promotes better adhesion during subsequent coating processes. The increased surface roughness provides a greater surface area for the coating material to adhere to, resulting in improved bond strength and durability. This is particularly important for the protective paint coatings applied to the cylinders to enhance corrosion resistance. Following shot blasting, the cylinders may undergo additional surface treatments to further enhance their corrosion resistance and provide a suitable base for paint adhesion. After the paint on the gas cylinders has dried, the manufacturing process progresses to the valve installation stage. The valve is a crucial component that serves as the interface between the cylinder and the end user. The valve installation process requires precision and attention to detail. Highly skilled technicians handle this task to ensure proper alignment and tight sealing between the valve and the cylinder. Once the valve is installed, it undergoes rigorous quality testing to ensure its proper functionality and leak-free operation. This testing is essential to guarantee the integrity and safety of the gas cylinders. Pressure tests involve subjecting the valve and cylinder assembly to elevated pressures to verify that it can withstand the intended operating conditions without any leaks or failures. Once the individual components of the cylinder are prepared, they are assembled together. This includes attaching valves, pistons, seals, and other necessary parts. Skilled technicians carefully follow assembly instructions and quality control protocols to ensure proper fit, alignment, and functionality of the cylinder. After assembly, the cylinders undergo rigorous testing to ensure they meet the required performance standards. Common tests include pressure testing, and functional testing. These tests verify the cylinder's ability to withstand the intended operating conditions and perform reliably. Quality control is an integral part of the manufacturing process. Chinese factories often implement robust quality control systems to ensure that each cylinder meets stringent quality standards. Inspections are conducted at various stages, including material inspection, in-process inspection, and final inspection. These inspections involve dimensional measurements, visual examinations, and performance evaluations to identify any defects or deviations from specifications. Before painting, the surfaces of the spray paint bottles need to be properly prepared. This typically involves cleaning and degreasing the bottles to remove any dirt, oil, or contaminants that could affect the paint adhesion. Surface preparation may also include sanding or buffing to smoothen any imperfections or rough areas on the bottle surface. Priming is an optional but often recommended step in the painting process. Primers create a smooth and uniform surface for the paint to adhere to, enhance adhesion, and improve the overall finish. Primers are typically applied in a thin layer using techniques such as spraying or dipping. The primed bottles are then allowed to dry or undergo a curing process, depending on the specific primer used. Once the priming stage is complete, the spray paint bottles are ready for the application of the desired paint color or coating. The paint can be applied through various methods such as spraying, dipping, or electrostatic painting, depending on the manufacturing requirements and the scale of production. Spraying is a common method used for painting spray paint bottles. It involves using spray guns or automated spray systems to evenly apply the paint onto the surface. The bottles are placed on a conveyor system or held in fixtures, allowing the paint to be applied from different angles for complete coverage. The spraying process requires precise control of paint flow, pressure, and nozzle settings to achieve consistent and uniform results.
The process begins with the acquisition of high-quality billets that meet various national and international standards. These billets serve as the raw material for the production of dependable steel bars. The heart of AKS's steel production is its state-of-the-art thermal mechanical treatment technology. This technology revolutionizes the steel bar production process in Bangladesh. It starts by heating the billets in a reheating furnace, ensuring the proper temperature for the subsequent rolling process. The rolling mill, segmented into 3 parts, is a key component. What sets AKS apart is its combination of horizontal and vertical stands in the rolling process. This innovative approach eliminates the need for continuous turning of billets, which can weaken the steel's inner structure. This sequence of shaping the billets ensures increased material density and strength. A computerized micro-tension control system maintains constant tension throughout the steel bar production process, further ensuring quality. After rolling, the steel bars undergo a high-speed thermomechanical treatment process, followed by a cooling system that creates temperature differences between the core and surface, resulting in layered steel bars known as DMT steel bars. The impressive 120-meter-long cooling bed at AKS is a critical component of their steel production process. This extensive cooling bed allows for a gradual and controlled cooling of the freshly rolled steel bars. As the steel bars move along this bed, they cool and solidify, a crucial step in enhancing their structural integrity. Automated machines are strategically employed at the end of this cooling bed to bind the finished steel bars. These machines play a pivotal role in ensuring uniformity and safety in the final product. By automating this process, AKS can guarantee consistent quality across all their steel bars, reducing the risk of defects and strengthening the overall structural integrity of the construction materials they produce. This commitment to precision and safety underscores AKS's dedication to delivering top-tier steel products to the market. Quality control is paramount at AKS. Their state-of-the-art quality laboratory rigorously tests the physical, chemical, and mechanical properties of the steel bars to ensure they meet both national and international standards. In particular, AKS prides itself on achieving an elongation capacity of 22%, far surpassing the standard for regular steel bars in Bangladesh.
Repkon is a renowned and globally recognized provider of industrial automation solutions, specializing in the design and manufacture of innovative LPG liquefied petroleum gas cylinder welding machines. The neck ring, which provides a connection point for the valve, is welded to the top end of the cylinder. The valve is then installed securely into the neck ring. The valve is responsible for controlling the flow of LPG into and out of the cylinder. The neck ring, typically made of brass or other suitable material, is welded to the top end of the cylinder. The neck ring provides a connection point for the valve and ensures a tight seal between the valve and the cylinder. Once the neck ring is securely welded, the valve is installed into the neck ring. The valve is a crucial component responsible for regulating the flow of LPG into and out of the cylinder. During the valve installation process, special care is taken to ensure a proper seal between the valve and the neck ring. This is crucial to prevent any gas leaks that could pose a safety hazard. Welding plays a crucial role in the production process of LPG cylinders, as it involves joining the cylinder body and bottom end to create a seamless and leak-proof container. The welding process typically employs a combination of electric resistance welding and submerged arc welding techniques. Electric resistance welding (ERW) is commonly used to join the cylinder body and bottom end. This method involves passing an electric current through the metal components to generate heat, which melts the edges to be joined. The molten metal is then fused together to form a solid bond. ERW ensures a strong and durable joint between the cylinder body and bottom end. Submerged arc welding saw is another technique employed in the welding process. It involves the use of a consumable electrode and a flux layer to shield the welding area from atmospheric contamination. The welding arc is generated beneath the layer of powdered flux, which melts to form a protective slag and shields the weld zone. SAW provides excellent penetration and deposition rates, resulting in a robust and reliable weld between the cylinder body and bottom end. Both ERW and SAW techniques are carefully controlled to ensure the welds meet specific quality standards and regulations. Skilled welders and automated welding machines are utilized to maintain consistency and precision during the welding process. After the welding process, the LPG equipment goes through a heat treatment phase. Heat treatment involves subjecting the metal components to controlled heating and cooling cycles to enhance their mechanical properties. This process helps eliminate residual stresses, improve the material's strength, and increase its resistance to corrosion. The heat treatment process typically includes heating the components to a specific temperature and then holding them at that temperature for a defined period. Afterward, the components are gradually cooled down to room temperature. This controlled heat treatment ensures the desired metallurgical structure and properties, making the LPG equipment more durable and reliable. Once the welding and heat treatment processes are complete, the LPG equipment moves to the hydrostatic testing line. Hydrostatic testing is a crucial step in ensuring the integrity and safety of the equipment. This test involves pressurizing the equipment with water or another suitable liquid to verify its resistance to leaks or ruptures. During the hydrostatic testing process, the LPG equipment is filled with water and pressurized to a predetermined level. The equipment is then inspected for any signs of leakage or structural weaknesses. This rigorous testing helps identify any potential flaws or defects that could compromise the equipment's safety. Only equipment that passes this testing phase moves on to the next step. Shot blasting is an important process used in the surface preparation of LPG equipment in the manufacturing of the Repkin LPG production finishing line. Shot blasting involves propelling high-speed abrasive materials, such as steel shot or grit, onto the surface of the equipment using compressed air or centrifugal force. The abrasive particles strike the surface of the equipment, removing impurities, rust, scale, and other contaminants. This process not only cleans the surface, but also creates a roughened texture, which promotes better adhesion of coatings and finishes. Shot blasting effectively prepares the surface by improving its cleanliness, roughness, and overall quality, ensuring optimal coating adhesion and enhancing the durability and longevity of the LPG equipment. Before the wet painting process begins, the LPG equipment undergoes thorough cleaning to remove any contaminants or residues that could affect the adhesion and quality of the paint. This cleaning may involve processes such as degreasing, washing, and drying. Once the equipment is properly cleaned, it moves through the wet painting line, where automated or manual spray guns are used to apply the liquid paint coatings. During the painting process, the spray guns release a controlled amount of paint onto the equipment's surface, creating a smooth and consistent layer. After the paint is applied, The equipment is then moved to a curing oven, where it undergoes a carefully controlled heating process. The oven temperature and duration are set according to the paint manufacturer's specifications to allow the paint to cure properly and form a durable finish. Quality control is a critical aspect of the wet painting line. The painted equipment is thoroughly inspected for any imperfections, such as color inconsistencies, drips, or surface defects. Any defects identified are rectified, either through manual touch-ups or by sending the equipment back for rework. The wet painting line ensures that the LPG equipment not only has a visually appealing appearance, but also possesses a protective coating that safeguards it against corrosion and extends its service life. The proper application of paint in this stage contributes to the overall quality, aesthetics, and longevity of the Repkin LPG production finishing line. The proper application of paint in this stage contributes to the overall quality, aesthetics, and longevity of the Repkin LPG production finishing line. The final step in the manufacturing process of the Repkin LPG production finishing line is the surface coating and finishing line. This step involves applying protective coatings and finishes to enhance the equipment's aesthetics, durability, and resistance to corrosion. The surface coating process begins with thorough cleaning and preparation of the LPG equipment's surface to ensure proper adhesion of the coating material. Once the surface is prepared, a suitable coating material is applied. This could be a paint or a specialized protective coating, depending on the specific requirements of the LPG equipment. After the coating is applied, the equipment undergoes a finishing process, which includes inspection, quality control, and any necessary touch-ups or adjustments. The manufacturing process of the Repkin LPG production finishing line encompasses several essential steps. These steps, including welding, heat treatment, hydrostatic testing, and surface coating.
The knife manufacturing process kicks off with the auto-cutting stage. High-grade steel sheets, typically composed of stainless or carbon steel, are loaded into machines equipped with precise cutting tools. After cutting, the knife blanks are subjected to sand injection. This step involves blasting fine abrasive particles at the knife's surface. Next, the blanks are placed in an oven for tempering. Tempering is a critical step in the knife-making process, as it strengthens the steel and improves its hardness. Once tempered, the blanks are moved to a CNC, computer numerical control, hammering machine. CNC technology allows for precise shaping of the knife blade. After hammering, the blades are subjected to profile cutting. This step defines the knife's final shape, including the edge, spine, and handle. Following profile cutting, the knife blades undergo side grinding. Knife blades are then subjected to grinding, which sharpens the edge to razor-like precision. To give the knife its distinctive shape and add ergonomics to the handle, the blade is pressed into the handle material. This step is crucial for both the knife's functionality and aesthetics, as it forms a seamless transition between the blade and handle. After pressing, the blade undergoes another round of grinding, primarily focused on honing the edge to perfection. This step ensures that the knife is exceptionally sharp and ready for use. To enhance the knife's appearance and remove any surface imperfections, side polishing is performed. This step gives the blade a mirror-like finish and elevates the overall aesthetics of the knife. The final step involves thorough cleaning and washing of the knives. This not only removes any residual materials, but also ensures that the knives are free from contaminants and ready for packaging and distribution.
The first step is the extraction of iron ore from mines. Iron ore is a natural resource found in the Earth's crust and is typically mined in large open pit or underground mines. The extracted iron ore undergoes processing to remove impurities and improve its quality. This involves crushing the ore into smaller pieces and then using various techniques such as magnetic separation, flotation, and gravity separation to separate the iron from other minerals. The processed iron ore is then smelted in a blast furnace. In the blast furnace, iron ore, along with coke, a form of coal and limestone, is heated to high temperatures. The pig iron obtained from smelting is further processed in a steelmaking furnace, typically a basic oxygen furnace BOF, or an electric arc furnace EF. In the BOF process, oxygen is blown through the molten pig iron to oxidize impurities, resulting in the production of steel. Once the steel is produced, it is cast into large, rectangular-shaped blocks called billets or slabs. Casting is done by pouring the molten steel into a mold and allowing it to cool and solidify. The billets or slabs can vary in size, depending on the desired final product. The steel plates or sheets are subjected to a heat treatment process to improve their mechanical properties, such as strength and toughness. This involves heating the steel to a specific temperature and then cooling it rapidly or gradually, depending on the desired characteristics. The heat-treated steel plates or sheets are then cut into the desired shape and size for leaf spring production. These materials are chosen for their excellent mechanical properties, including high tensile strength and resilience. The steel is obtained in the form of coils or flat bars, which are carefully selected based on their quality and specifications. The selection process considers factors such as chemical composition, uniformity, and surface condition. The raw material quality plays a crucial role in determining the overall strength and performance of the leaf springs, ensuring that they can withstand heavy loads and provide reliable suspension for vehicles. In this step, the raw material is straightened to remove any deformations or bends. The coil or flat bar is passed through a series of rollers and presses, exerting force to reshape the material into a straight form. This process ensures uniformity and consistency in the leaf spring's shape. The next step in the manufacturing process of leaf spring suspension is tapering the leaf spring to achieve the desired shape. Tapering refers to the gradual reduction of the width of the leaf from the center towards the ends. Tapering is performed to ensure that stress is distributed evenly along the spring. As the width decreases towards the ends, the material thickness increases proportionally. This tapering design helps to prevent localized stress concentrations, which can lead to cracking or failure of the leaf spring. To accomplish tapering, specialized machinery is used. This machinery is designed to apply controlled pressure on the leaf spring, gradually reducing its width. The leaf spring is passed through a series of rollers or presses that exert force on the material, reshaping it into the tapered form. The machinery ensures precision and consistency in achieving the desired tapering profile. The tapering process involves careful calculation and engineering to determine the appropriate taper ratio. The taper ratio refers to the rate at which the width of the leaf spring decreases along its length. The controlled pressure applied during tapering not only adjusts the width, but also affects the curvature of the leaf spring. Tapering plays a crucial role in improving the flexibility and load-carrying capacity of the leaf spring. The gradual reduction in width results in a progressive change in the leaf stiffness along its length. Once the leaf springs have been tapered, they need to be efficiently transported to the subsequent stages of the manufacturing process. To facilitate this, an automatic conveying system is employed, which plays a vital role in maintaining the workflow and minimizing manual handling. The automatic conveying system consists of a series of conveyor belts, rollers, or other mechanical devices that are strategically positioned throughout the manufacturing facility. The leaf springs, after tapering, are carefully placed onto the conveyor system, either manually or through automated loading mechanisms. The system is equipped with sensors and controls to detect and regulate the movement of the leaf springs. The automatic conveying system offers several advantages. First and foremost, it improves efficiency by eliminating the need for manual handling and transportation of leaf springs. Moreover, the automatic conveying system helps in maintaining the quality of the leaf springs. Manual handling can sometimes lead to accidental damage or mishandling, which can affect the integrity of the leaf springs. By using automated conveyors, the risk of such damage is significantly reduced, as the leaf springs are securely and consistently transported without unnecessary jostling or impacts. The conveying system is designed to handle leaf springs of various sizes and weights, accommodating the specific requirements of the manufacturing facility. Quenching is a critical step in the heat treatment process of manufacturing leaf spring suspension. Once the tapered leaf springs have been shaped, they undergo a controlled heating process. The leaf springs are heated to a high temperature, typically above the austenitizing temperature of the steel. After the desired temperature is reached, the heated leaf springs are rapidly cooled by immersion in a quenching medium. The most commonly used quenching media for leaf springs are oil or water. The rapid cooling during quenching induces a transformation in the steel known as martensite formation. By hardening the steel, quenching significantly improves the load-carrying capacity and durability of the leaf springs. However, it is important to note that the rapid cooling during quenching can introduce internal stresses in the leaf springs. These residual stresses can potentially lead to cracking or distortion. After quenching, the hardened leaf springs are tempered to relieve internal stresses and improve their toughness. Tempering involves reheating the leaf springs to a specific temperature and holding them at that temperature for a predetermined period. Once the leaf springs have undergone the heat treatment and tempering processes, they are ready for assembly. Leaf spring suspension systems typically consist of multiple leaves that are stacked on top of each other and held together by center bolts. The leaves are arranged in a specific order, with the longest and thickest leaf positioned at the bottom, providing the primary support. During assembly, the leaves are carefully aligned to ensure proper fitment and functionality. Special attention is given to aligning the eyes or holes in each leaf, as they will serve as attachment points for the suspension system. Clamps or retaining plates are used to secure the leaves together, preventing any movement or separation during operation. The center bolt is inserted through the aligned holes in the leaves and tightened to provide additional stability to the assembly. Quality control is an essential aspect of leaf spring manufacturing to ensure the longevity and performance of the suspension system. To evaluate the fatigue resistance of the leaf springs, a sample is subjected to fatigue life testing. This involves applying cyclic loading and unloading forces to simulate the real-world conditions the leaf springs will experience during vehicle operation. During fatigue life testing, the leaf springs undergo repeated cycles of loading and unloading, while their behavior and response are closely monitored. This testing is typically conducted using specialized testing equipment that applies controlled forces to the leaf springs. The number of cycles and the applied loads are determined based on industry standards and the specific requirements of the leaf spring design. By subjecting the leaf springs to fatigue life testing, manufacturers can assess their durability and identify any potential weaknesses or flaws in the design or manufacturing process. This helps ensure that the leaf springs meet the required performance standards and can withstand the expected loads and stresses over their operational lifespan. After passing the quality control tests, the leaf springs are marked with relevant information for identification and traceability purposes. This marking typically includes part numbers, specifications, manufacturing dates, and other relevant details. The final step in the manufacturing process is the loading of the finished leaf springs into containers for transportation to distribution centers or customers. Proper container loading is crucial to prevent any damage during transit.
To prepare the ingot for rolling and establish its metallurgical properties, preheating is performed. Kaiser Aluminum Warwick employs 2 pusher furnaces for this purpose. Once pliable, the rolling process commences at the reversing mill. Large rollers, powered by 2 robust 7,000 horsepower motors, reduce the thickness of the ingot through a back-and-forth motion. The initial stage of hot rolling, executed at temperatures around 900 degrees Fahrenheit, leads to a reduction in thickness from 21 inches to 1.5 inches, while also elongating the ingot from 30 feet to a remarkable 400 feet. Continuing with the hot rolling process, a flying shear severs the head and tail of the aluminum slab, marking the transition to the 6-stand continuous mill. Here, the metal is further flattened, achieving a thickness of 1/8 of an inch. The culmination of this stage sees the aluminum coiled for the first time, resulting in coils that can span up to approximately 1 mile in length. The subsequent phase, cold rolling, takes place after the metal has cooled down to temperatures between 200 to 300 degrees Fahrenheit. The aluminum proceeds to one of Kaiser Warwick's cold mills. In this environment, the metal undergoes further reduction in thickness, all while traveling at speeds nearing 60 miles per hour. Exiting the cold mill, the aluminum reaches an incredibly thin dimension, measured in thousandths of an inch. Upon completion of the rolling process, the ingot, which once started as a 30-foot-long, 21-inch thick block of metal, is now transformed into a coil that, if unraveled, could extend up to 10 miles in length. Waste computer board recycling plant. In our modern digital era, electronic waste, e-waste, has become a significant concern due to its adverse environmental impact. To address this issue, waste computer board recycling plants have emerged as crucial facilities for recycling and recovering valuable materials from discarded electronic devices. These plants employ various machines and processes to dismantle, crush, separate, and screen electronic components and printed circuit boards, PCBs, to extract valuable resources while minimizing environmental harm. PCB dismantling machine, remover components. One of the initial steps in the recycling process is the PCB dismantling machine, which efficiently removes electronic components from waste PCBs. This machine utilizes advanced technologies and tools to disassemble the circuit boards, ensuring the safe removal of valuable components while minimizing damage to the components themselves. Waste electronic components. After the PCBs are dismantled, the next step is to deal with the waste electronic components. These components, such as resistors, capacitors, and integrated circuits, may still hold value and can be reused or sold for secondary purposes. Separating and sorting these components is essential for maximizing resource recovery and minimizing waste. Waste PCB motherboards. The waste PCB motherboards, once stripped of their electronic components, undergo further processing. These motherboards contain precious metals like gold, silver, and palladium, as well as copper and other recyclable materials. Proper handling and processing of these boards are necessary to extract these valuable resources in an efficient and environmentally friendly manner. PCB motherboards, crushing and separating machine. To extract the valuable materials from waste PCB motherboards, a crushing and separating machine is employed. This machine breaks down the boards into smaller pieces, facilitating subsequent separation processes. The crushed PCBs are then fed into the machine, which utilizes mechanical and physical methods to separate different materials based on their properties. First separation. Copper powder. The first step in the separation process focuses on extracting copper from the crushed PCBs. The crushed boards are subjected to mechanical processes such as vibration and airflow separation to separate the copper from other materials. Through these methods, copper powder is obtained, which can be further processed for purification and reuse. Second separation. Copper powder and resin powder. In the second separation stage, the remaining materials, including resin powder, are further processed to recover additional valuable resources. Advanced separation technologies, such as electrostatic separation and magnetic separation, are employed to separate the copper powder from the resin powder. These processes enable the efficient recovery of both materials for subsequent reuse or recycling. Electronic components screening machine. Once the PCBs are crushed and the valuable materials are separated, the electronic components obtained earlier in the process undergo a screening phase. An electronic components screening machine is used to sort and categorize these components based on their condition and quality. This ensures that functional and reusable components are identified for potential resale or reuse, while damaged or non-functional components are properly disposed of or recycled.
The first step in the manufacturing process is the design and material selection phase. Engineers and designers work together to develop an optimal design that meets safety standards and regulatory requirements. The P50 composite extinguisher is typically made from a combination of lightweight composite materials, such as aramid fiber reinforced polymer, which provides high strength and durability. The cylinder is a crucial component of the P50 composite extinguisher. The manufacturing of the composite cylinder involves several steps. First, the composite material is prepared by combining resin and reinforcing fibers. This mixture is then wound around a cylindrical mandrel in a precise pattern to ensure uniform strength and thickness. The wound composite is then cured in an oven to harden the resin and create a rigid structure. Once the composite cylinder is manufactured, the next step is to install the valve assembly. The valve serves as the control mechanism for discharging the extinguishing agent. Skilled technicians carefully install the valve onto the cylinder, ensuring a secure and leak-proof connection. The valve is typically made from durable materials such as brass or stainless steel, to withstand high pressure and corrosive environments. After the valve installation, the composite cylinder undergoes rigorous pressure testing to ensure its integrity and safety. The cylinder is pressurized to a specific level, and it must hold the pressure for a specified duration without any leakage. Once the composite cylinder passes the pressure testing, it is ready for the filling of the extinguishing agent. The type of extinguishing agent used depends on the intended application of the P50 extinguisher. Common agents include water, foam, or dry chemical powders. The filling process is carried out with precision to ensure accurate quantities of the extinguishing agent are added. After the extinguishing agent is filled, the P50 composite extinguisher undergoes final assembly. This includes attaching the discharge hose and nozzle, pressure gauge, and safety pin. Each component is carefully inspected and tested to ensure proper functionality and adherence to quality standards. The extinguisher is also visually inspected for any cosmetic defects or imperfections. After the extinguishing agent is filled, the P50 composite extinguisher undergoes final assembly. This includes attaching the discharge hose and nozzle, pressure gauge, and safety pin. Each component is carefully inspected and tested to ensure proper functionality and adherence to quality standards. The extinguisher is also visually inspected for any cosmetic defects or imperfections. Once the manufacturing process is complete, the P50 composite extinguishers are packaged and prepared for distribution. They are typically packed in protective cartons or cases to prevent damage during transportation. Labeling and instructional materials are included to provide users with essential information on operating the extinguisher effectively.